In the southern sky there is a star system so close that every serious discussion about the future of space exploration begins there. Alpha Centauri, about 4 light-years away. That number sounds almost manageable. 4 years. Close enough to feel like an invitation. But here is the problem. Light itself needs more than 4 years to make that crossing. The fastest spacecraft we have ever launched would need around 73,000 years. Look closer, and it stops being a trip. It becomes a physics problem we do not yet know how to solve. Tonight we are going to treat Alpha Centauri as a real destination. Not a symbol, not a vague promise. A place with a specific distance, a specific set of constraints, and a series of hard questions that do not go away no matter how optimistic we try to be. Because nearest does not mean reachable. And 4 light-years is not a distance we know how to cross. It just sounds like one. By the end of tonight, we will know exactly why. We will follow every layer of the problem in sequence, from distance to travel time, from travel time to communication, from communication to braking, from braking to shielding, and from shielding to the deeper question of what kind of mission survives all of it, with anything useful still intact. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. The first trick Alpha Centauri plays on us is a linguistic one. We hear the phrase nearest star system and our minds quietly translate it into something like first destination. Not easy, not casual, but available in principle. The phrase suggests a ranking, and rankings suggest mercy. Out of all the stars, this is the one that gives us the best chance. But here is the thing. Nearest is an astronomical comparison, not a transportation promise, and we can feel the difference if we slow down for a moment. When we call something the nearest mountain or the nearest city, we are still talking about places that belong to a travel world we already know how to cross. Even the nearest island belongs to that same family of motion. Alpha Centauri smuggles that familiar feeling into a place where it no longer applies. Now think about what the word does emotionally. It smooths the problem. It tells us there is a first rung on the ladder. It suggests that interstellar space begins gently, maybe not comfortably, but with one approachable case, one destination that sits just beyond the outer edge of what we can currently reach. But nature has not arranged the stars that way. And we need to be careful here because the trap is subtle. The number is not hidden. Anyone can look up that Alpha Centauri is about 4 light-years away. The problem is that the human mind does not hear 4 light-years as a travel sentence. It hears it as a map sentence. The distance remains geometric. It has not yet turned into travel time or mission risk or engineering architecture. So we build the wrong intuition without even noticing. We start imagining the first interstellar mission as an upgraded version of what we already do. A bigger launch, a more advanced engine, a longer cruise, maybe a harder life support problem, maybe a project for a later century, but still the same basic shape of thought. And that is exactly what Alpha Centauri punishes, because it is not merely farther than Pluto, and it is farther than the Oort cloud. It sits on the other side of a boundary where familiar mission problems stop scaling gracefully. Travel time becomes civilizational. Communication delay becomes operational isolation. Speed becomes a shielding problem. Arrival becomes a braking problem. Payload mass becomes a verdict on what kind of mission is even imaginable. Now look at the mental picture most people carry. Local star maps are often shown as points in a neat neighborhood. The Sun here, Alpha Centauri there, a few others scattered nearby. The whole arrangement feels ordered, legible, almost nautical, as if the stars were islands on a chart and our only challenge were building a tougher ship. But those maps preserve geometry while erasing cost. A map can tell us what is nearby in relative terms, without telling us what the crossing costs in time, energy, or risk. It does not make us feel the years, the power demand, or the strain on hardware and institutions. So Alpha Centauri gets to keep the emotional benefits of familiarity without paying the engineering bill. It looks like a place, it sounds like a name we already know, and before we notice, we have started treating it like a very long trip. And a long trip is still part of a world we understand. A long trip means more fuel and more patience. It means a harder version of something known. Alpha Centauri is valuable as a documentary subject precisely because it starts out looking like that and then refuses to cooperate. The deeper we follow the problem, the more the destination stops being a harder road and starts becoming a different class of physical challenge altogether. So the right opening move is not to declare that the stars are very far away, and that is too vague to be useful. The right move is to notice exactly where our ordinary language fails. Nearest sounds like a practical category, but it is not, and it is only a ranking inside astronomy. It says nothing about whether travel remains intelligible on human terms. And we can feel that gap most clearly by looking at where the phrase comes from and what it actually describes. Alpha Centauri is the closest stellar system to our own, and that is a genuine astronomical fact. But closeness in astronomy is measured in units that our bodies and our intuitions were never calibrated to handle. 4 light-years is tiny compared to the Milky Way, and it is enormous compared to anything our civilization has ever attempted. So when we say nearest, we need to immediately ask, nearest on which scale? Nearest on the galactic map, yes. Nearest in a way that makes travel meaningfully approachable. And that is the question this whole video is built around. And here is what makes Alpha Centauri the right place to ask it. But it is not a threatening or unusual example, and it is the most generous case nature offers. If we can show that even this example breaks our comfortable assumptions, then the lesson is not about one awkward star. The lesson is about the structure of the universe itself. Now there is one more thing worth saying here before we even ask what Alpha Centauri actually is. The nearest star trap has a cultural dimension too. Alpha Centauri appears in books, school lessons, and science fiction often enough that it starts to feel almost domestic. We know the name before we know what the crossing costs. And once a destination feels culturally familiar, the mind tends to assume that technology will eventually catch up to the imagination. But familiarity in language is not familiarity in physics. The star system does not become more approachable because it has been living in our imagination for a long time. So one of the quiet jobs of this video is to reverse that domestication. We are taking something that sounds almost friendly and returning its physical edges to it. Not to make it dramatic for drama's sake, to make it honest. The nearest star should not feel like a vague symbol of future progress. It should feel like the first place where progress meets a barrier large enough to change what progress means. Now let's stay with the trap a little longer, because it runs deeper than just one misused word. The nearest star trap is not really about the word nearest, and it is about how we process scale. Human beings are built for a fairly narrow range of spatial experience. We understand the distances our bodies can travel in a day. We extend that to the distances our vehicles can cross in a lifetime. We stretch it a little more with telescopes and spacecraft, but at some point the numbers simply stop connecting to anything visceral. They become decorative. They sit in our memory like labels rather than measures. And interstellar distances are far enough outside our calibrated range that the labels do almost all the emotional work. 4 light-years get stored in memory next to numbers like 4 miles or 4 hours. It carries the emotional weight of smallness because the numeral is small, even though the unit is enormous. Now think about why that matters for how we talk about the future. If we hear that a new propulsion concept could get to Alpha Centauri in 20 years, and we have already stored 4 light-years as a short number, the 20-year figure feels like confirmation that the problem is basically solved. The number and the unit connect to form a feeling of progress. But that feeling is a function of how we store information, not of what the physics is actually saying. And this is not a problem unique to general audiences. It shows up in scientific communication too. Research papers and mission studies sometimes present optimistic time estimates in ways that make sense internally, under a specific set of favorable assumptions for a specific narrow class of mission, but that get extracted from those contexts and used to support much broader claims. Alpha Centauri is the clearest test of whether a claim has survived that extraction or been corrupted by it. Because the claim always has to answer the same battery of questions: what mission class, what payload, what propulsion system, what communication plan, what braking strategy, what are the particle damage assumptions at the required speed, what does institutional continuity look like over the required timescale. A claim that cannot answer those questions has not yet made contact with the physical problem. It has made contact with the emotional one, and that is fine in its place. Emotional contact with ambitious ideas matters, but it is a starting point, not an end point. The nearest star is where the starting point has to become something more rigorous if the conversation is going to stay honest. And once we start hearing the word nearest that way, everything that follows locks into place. Every constraint we will look at tonight is really an explanation of that one mismatch between what the language suggests and what the physics actually demands. Most people hear Alpha Centauri and picture one bright nearby star. That makes sense. The name sounds singular. Popular astronomy often treats it as shorthand, and for a casual conversation, that shorthand is good enough. But it is not good enough for a video about reachability, because mission logic depends on target logic, and the target is more complicated than the name. Alpha Centauri is actually 3 objects. Alpha Centauri A and Alpha Centauri B form a binary pair. They orbit a shared center of mass over a period of about 80 years, and at closest approach they come within a distance roughly comparable to Saturn's orbit around the Sun. When we look up from Earth and see Alpha Centauri as a single bright point, we are looking at that binary pair combined. The 2 stars are close enough that separating them requires a proper telescope. To the naked eye, they arrive as one. Now Alpha Centauri A is the larger of the 2, and it is a G-type star, broadly similar in size, temperature and luminosity to our own Sun, though slightly more massive and a little brighter. B is a K-type star, smaller and cooler, still a proper main sequence star by every standard that counts. And then there is Proxima Centauri. Proxima orbits the A and B pair at an enormous distance, perhaps a quarter of a light year out, carrying a period of roughly 500,000 years per orbit. And it is a red dwarf, small and dim, and it holds the title of the single closest star to the Sun. Proxima is about 4.24 light-years from us. Alpha Centauri A and B are very slightly farther, about 4.37 light-years. Those differences are genuinely small in cosmic terms, but they matter for mission design in ways we will come back to. Now here is why the distinction between the 3 members matters. Proxima has planets. We know of at least one in what is sometimes called the habitable zone, Proxima b, and possibly others. That makes it an attractive target for any probe interested in planetary science or biosignatures. But Proxima also has a problem, and it is a flare star. It periodically releases intense bursts of ultraviolet and X-ray radiation that would strip the atmosphere of an unprotected planet and bombard any surface with sterilizing energy. Whether Proxima b is genuinely habitable is far from settled. Its star makes that question genuinely difficult. Alpha Centauri A and B are calmer. They share the temperature and stability profile that we already associate with a Sun-like environment. Both have been proposed as potentially hosting planets, though confirmed detections have been harder to establish for this pair than for Proxima. So the system already presents us with a choice. Do we aim for the closest member, with its confirmed planets but violent radiation environment? Or do we aim for the slightly more distant but calmer pair, where conditions for complex atmospheres seem more plausible? But that is not a problem we have to solve tonight. But we should hold it in mind. Even naming the destination requires that we know which of the 3 objects we mean, and each choice carries different mission geometry, different science priorities, and different surface conditions for any probe or future explorer to contend with. Now let's hold on to one more thing about the system before we move to distance itself. The Alpha Centauri pair is not sitting still relative to us. Stars move. The whole system is drifting through the galaxy on its own path. Over very long timescales, tens of thousands of years, the distance between us and Alpha Centauri will change. For now, the system is actually approaching us very slowly. In about 25,000 years, it will be at closest approach before beginning to draw back outward, but that is not relevant to near-term mission planning. But it is a reminder that the universe is not a fixed map. The stars are objects in motion, and any serious long-term conversation about interstellar travel has to treat the destination as a moving target. For now, though, 4 light-years, 3 objects, a binary pair and a dim red companion. And that is what we are actually talking about when we say Alpha Centauri. Now let's spend a little more time on what the structure of the Alpha Centauri system means for any probe or mission aimed at it. The binary nature of Alpha Centauri A and B creates a dynamically interesting region. 2 stars in a mutual orbit around a shared center of mass creates a more complex gravitational landscape. Any planets in the system have to navigate something our solar system planets never encounter. A planet orbiting close to A or close to B would be dominated by one star's gravity, similar enough to our solar system that stable orbits are possible. But orbit farther out, where the pull of both stars becomes roughly comparable, and the environment grows more chaotic. Stable orbits over billions of years become harder to maintain. This matters for the habitability question. The region close to each star individually is gravitationally stable, but the system does not offer the same kind of generous outer zone that our own Sun does. The influence of the binary companion complicates disk formation and planetary orbital dynamics in ways that may have affected what kinds of worlds could form and where. And for Proxima specifically, the habitability story involves a different kind of complication. Proxima b, the planet in the nominal habitable zone, orbits its star at about 0.05 astronomical units. Our Earth orbits at 1 astronomical unit. Proxima b is much closer because Proxima is a much cooler star, so the region where liquid water could exist on a surface is correspondingly closer in. But that proximity has its own problems. At such a close orbit, the planet is likely tidally locked. One face permanently toward the star, one face permanently away. That creates extreme temperature differences between the 2 hemispheres. The day side could be searingly warm. The night side could be permanently frozen. Whether atmospheric circulation could moderate those extremes is an active area of research with no settled answer. And then there is the flaring. Proxima releases powerful bursts of radiation that could, over geological timescales, strip away a planetary atmosphere that lacks strong magnetic protection. Whether Proxima b has such protection is unknown. Red dwarfs like Proxima are magnetically active, especially when young. Their flare histories may have shaped the environments of any nearby planets in ways we cannot yet measure precisely. So the question of what a probe would actually find at Alpha Centauri, and specifically what it would find at Proxima, is genuinely open. The system offers more science targets than a single nearby star. It also offers more uncertainty about what those targets look like up close. And that scientific richness is part of why the mission is worth thinking about seriously, even given the enormous physical challenges. The system may host worlds. Those worlds may be measurable, and whatever they turn out to be, those measurements would reshape our understanding of planetary formation and habitability in binary and red dwarf environments. Remote observation from Earth could never quite replicate what a probe in that system could return. And now we need to ask what 4 light-years actually means in practice, because the number behaves very differently depending on how you approach it. 4 light-years is one of those numbers that the mind wants to accept too quickly. It sounds compact. It sounds like a number that belongs in the same conversation as meaningful human timescales. But that feeling is mostly the word for doing emotional work that the unit light-year should be preventing. So let's build the distance from the ground up. A light-year is the distance that light, moving at about 300,000 kilometers per second, the fastest anything can travel in the universe, covers in 1 full year. That works out to roughly 9.46 trillion kilometers. Now 4 light-years is 4 times that, about 37.8 trillion kilometers. Written as a raw number, that figure starts to resist imagination in a useful way. 37.8 trillion kilometers does not feel compact. It does not feel like a stepping stone. It feels like what it actually is, an enormous gulf, even by astronomical standards within our own galactic neighborhood. But even large numbers can feel abstract if we leave them disconnected from motion, so let's connect them. Inside the solar system, we talk about distances in a way that still belongs to a human scale of operation. Months to Mars at current speeds, a year or so to Jupiter, decades for Voyager to reach the edges of the heliosphere. Those are long spans, but they are mission spans. A team can plan around them. A funding cycle can survive them. A career can see the results. Alpha Centauri breaks that continuity, and not by a small margin. We are not talking about extending the outer planet mission template a little further. We are talking about a gap so large that our fastest current spacecraft would take longer to cross it than all of recorded human civilization has existed, 73,000 years at Voyager speed. And that is the number, and we should not let it blur into abstraction. 73,000 years ago, modern humans were still in the early stages of colonizing the world. The oldest known cave paintings are about 45,000 years old. Agriculture is roughly 12,000 years old. The entire span from the first cities to the present day is less than 10,000 years. Voyager is crossing interstellar space at about 17.4 kilometers per second. And that is genuinely fast by everyday standards. It would circle Earth's equator in under 40 minutes, and it is the kind of speed that makes the outer solar system feel reachable on mission timescales. And it is catastrophically insufficient for the stars. Now compare that with another common measure. Proxima is roughly 268,000 astronomical units away. 1 astronomical unit is the average Earth-Sun distance, about 150 million kilometers. Neptune sits about 30 astronomical units from the Sun. Proxima is not another layer of the same family, and it is nearly 9,000 times farther than Neptune. So when popular astronomy puts the Sun and the nearby stars on the same diagram, the visual closeness is a function of scale compression, not genuine proximity. The diagram is accurate in relative terms, and it is profoundly misleading as a guide to what crossing the gap would feel like. And here is the deeper issue with the number. Human beings are not calibrated for exponential scale differences. We understand nearby motion by comparing it to the body, the road, the ship, the aircraft, the rocket. We extend understanding by analogy. But interstellar distance is far enough outside our inherited experience that the analogies stop working. Even our instinct that faster travel simply means more of the same thing stops working here. Because the number 4 light-years is not just a distance we need to cross, and it is the minimum distance at which an entirely new set of engineering problems enters the picture. Communication delay stops being minutes and becomes years. Speed requirements stop being aggressive and become physically punishing. The idea of oversight, of control, of repair, of rescue, all of these concepts start to dissolve when applied to a craft crossing 4 light-years. And there is one more thing to say about why the number fools us so reliably. The eye can reach Alpha Centauri. Light from that system arrives at our retinas every clear night. Vision implies a kind of practical nearness that is deeply wired into human cognition. Mountains on the horizon can be walked toward. Lights across a valley can be approached. The stars break that habit completely. Their light arrives easily while the source remains beyond any ordinary approach. Alpha Centauri is where that contradiction becomes hardest to ignore, because the source is as near as any star can be, and still nowhere near enough for anything we would recognize as travel. Now there is another way to make 4 light-years feel real that goes beyond raw numbers. Compare it with what we have already reached. Voyager 1 is currently the most distant human-made object. It has been traveling for more than 45 years. It crossed the heliopause, the boundary where the Sun's influence gives way to interstellar space, in 2012, about 18 billion kilometers from Earth. In astronomical units, that is roughly 123 AU, and Proxima Centauri is about 268,000 AU away. So Voyager 1, after more than 4 decades of travel, has covered less than 1/20th of 1% of the distance to the nearest star. Think about that from the perspective of a mission planner. Voyager is genuinely in interstellar space now. It has crossed the boundary, and it is outside the protective bubble of the heliosphere. But it is still so close to the Sun by interstellar standards that Alpha Centauri is not remotely in its future on any human timescale. The distance from the heliopause to Proxima is not a short remaining stretch after a long journey, and it is vastly larger than everything Voyager has already covered. That comparison makes the scale visceral in a way that light-years and trillions of kilometers alone do not, and it tells us something important about the gap between deep space capability and interstellar capability. Voyager is deep space, and it is genuinely remarkable, but it is not remotely close to Interstellar in any travel sense that matters for a mission aimed at another star. The two things are not points on the same curve, they are on different scales altogether. Now look at it from a time perspective. The fastest human speed ever achieved in a spacecraft was by the Apollo 10 command module during re-entry, which reached about 39,897 kilometers per hour. And that is roughly 11 kilometers per second, slower than Voyager's current outbound speed of about 17 kilometers per second. At Voyager's speed, the travel time to Proxima is around 73,000 years. At Apollo 10's peak speed, it would be longer still, but even at Parker Solar Probe's deepest encounter speed of about 690,000 kilometers per hour, roughly 190 kilometers per second, or about 11 times Voyager's speed, the travel time to Proxima is still around 6,500 years. So our fastest spacecraft, our deepest solar encounter, our most extreme speed record, all of them are still firmly in the category of nowhere near interstellar. We have not even gotten to the edge of the wrong order of magnitude, and that is the lesson. Not that we are close but need a little more engineering. We are separated from the nearest star by a gap whose crossing requires a level of performance so far beyond our current best that the problem is not incremental. And it is categorical, and there is a deeper reason 4 light-years fails to register correctly, and it is worth naming directly. Our intuition for large numbers was not built for astronomy. It was built for commerce, navigation, and human settlement. The largest distances our ancestors needed to feel in their bones were the distances between trading ports, mountain ranges, or continents. Those distances are measured in hundreds, or at most a few thousands of kilometers, numbers that the human brain over many generations learned to connect to experiences of travel time, physical effort, and geographic scale. The metric system extends that range somewhat. A kilometer is a unit we can feel. 10 kilometers is a walk of a couple of hours. 100 kilometers is a day's journey by foot. Even 1,000 kilometers begins to push at the edge of intuitive grasp. Above that, the numbers start becoming abstract. Labels rather than felt measures. A light year is roughly 9.46 trillion kilometers, and that is 12 orders of magnitude above 1 kilometer. The human brain has no evolutionary or cultural preparation for that scale. We cannot feel it the way we can feel a day's walk. We can only label it. And when we encounter a small numeral attached to that label, 4 in this case, the brain defaults to the emotional weight of the numeral, not the unit. And this is not a failure of intelligence, and it is a feature of how human cognition handles numbers. We are very good at relative comparisons within a range we have experience with. We are poor at absolute intuitions outside that range. And that is why science communication about interstellar distances is so difficult to get right. The right move is not to give people a bigger number that still floats free of experience. The right move is to anchor the large number to a concrete comparison that connects it back to something felt. 73,000 years of travel time connects to felt history in a way that 4.24 light-years does not. The distance equivalent to 268,000 Earth-Sun baselines connects to something spatial. The fact that our fastest spacecraft has been traveling for 45 years and still covers less than 1/20th of 1% of the distance connects the number to a real physical effort. Those are the kinds of anchors that help 4 light-years stop being a label and start being a measure. And building that genuine measure, that felt distance, is one of the most important things a video about Alpha Centauri can do, because without it, every later constraint seems like an engineering detail rather than what it actually is, an expression of how physically harsh the gap really is. So 4 light-years is not just a big number, and it is the first nearby sounding number that genuinely refuses to behave like a nearby destination. And once we hold that clearly in mind, every other constraint we are going to look at tonight starts making sense. There is no single travel time to Alpha Centauri, only scenarios. And that matters because the public conversation keeps trying to collapse the subject into one number. Someone asks how long it would take to get there. Someone offers a figure. the figure detaches from its assumptions, and before long we are no longer hearing science, we are hearing a mood. So let's build a ladder instead. Start with the cleanest benchmark from present reality. Voyager 1 is moving outward at about 17.4 kilometers per second, and that is already an extraordinary speed by everyday standards. And it is fast enough that it crossed the entire distance from Earth to the Moon's orbit in about 6 hours. But pointed at Proxima Centauri, Voyager would arrive in roughly 73,000 years, and Alpha Centauri A or B are a little farther still. Now that first rung matters precisely because it is real. Not a speculative propulsion concept. Not a future sketch, a genuine deep space speed achieved by a genuine spacecraft that is actually out there right now, still functioning, still sending data. And that rung alone tells us something brutal. Present-day interstellar travel does not give us a mission in any ordinary sense. It gives us a drift across epochs. Let's step up the ladder. What if we use the fastest speed humanity has actually achieved? The Parker Solar Probe reaches around 692,000 kilometers per hour on its deepest solar passes, about 190 kilometers per second, when it swoops closest to the Sun and uses the orbital dynamics to accelerate. That number sounds like it should change everything, but it changes less than we want. If we treat that peak speed as a sustained cruise toward Proxima, which Parker itself is not designed for and cannot maintain, we still get a travel time of roughly 6,600 years. 6,000 years is smaller than 73,000, yes, but it is not smaller in any way that makes it a meaningful mission timescale. 6,000 years ago, the wheel had only recently been invented. The pyramids at Giza were still 500 years in the future. Parker is useful precisely because it refuses to flatter us. It shows that even our most extreme present-day speed benchmark is still the wrong order of magnitude. Now we move to the optimistic probe case. Breakthrough Starshot is the concept that changes the timescale most dramatically. The idea is to accelerate a gram-scale light sail probe to around 20% of the speed of light using a vast ground-based laser array, gigawatts of focused laser power, all aimed at a sail no bigger than a postage stamp. Under that assumption, a flyby past Alpha Centauri becomes possible in just over 20 years. That number is genuinely different. 20 years is within a human planning horizon, and it is within a career, and it is within the period a government funding agency might recognize as connected to a single initiative. But it only becomes possible by changing almost everything else simultaneously. The payload shrinks to gram scale, the mass of a small paperclip. The mission becomes robotic by absolute necessity. The propulsion system moves entirely outside the craft, into kilometers of infrastructure on the ground. The encounter at the far end is a flyby. The probe races past its targets at a fifth of light speed, with no ability to slow down or change course. The entire concept is better understood as a demonstration of how much must be sacrificed to bring one narrow class of mission into human timescales, rather than as a general solution to interstellar travel. And that is exactly why Starshot matters. But it is not false hope, and it is a useful honesty test. If you want a few decades instead of millennia, the spacecraft stops looking like what our imagination usually means by spacecraft. Now let's look at Project Longshot, a serious historical mission study for a more substantial unmanned probe to Alpha Centauri, typically described as roughly a century-scale effort tied to fusion propulsion. Longshot is not current capability, but it is not near-term. But it occupies a middle ground that tells us something important. The moment we ask for a payload more substantial than a gram-scale chip, instruments that can do careful science, communications that can send back meaningful data, systems that can survive a century in transit, the mission time stretches back again, out of decades, into generations. So the ladder is not just a list of travel times, and it is a trade-off map. Voyager tells us what current deep space practice actually means. Parker tells us what record speed still fails to solve. Starshot shows how a 20-year benchmark demands ultralight payloads and immense external infrastructure. Longshot shows that once we insist on a more serious robotic architecture, the timescale grows back toward 100 years or more. Every rung answers a different question about what we are willing to give up. Faster missions do not simply cost more energy, they demand sharper compromises somewhere else. Smaller payloads, narrower science windows, higher vulnerability to particle damage, less room for redundancy, less room for braking. The trade does not have a free side, and we should sit with that pattern for a moment because it tells us something important about how to read speed headlines. A shorter travel time is not automatically better, and it is better only if the mission class that achieves it still does the work we care about. A 20-year flyby by a gram-scale probe is not doing the same job as a century-scale robotic observatory, and neither of those is doing the same job as a crewed mission. A travel time headline can compress all of that into a single feeling of progress. The physics cannot. So the honest question is never just, how long does it take to get to Alpha Centauri? The honest question is, how long does it take to send what kind of thing there, under what assumptions, and what kind of mission is left once those assumptions have been paid for? Now let's look at the travel time ladder one more time, from a different angle. Each rung is not just a speed. Each rung represents a different answer to the question, what are we willing to give up? Voyager-class speed gives up the timeline entirely. It preserves a recognizable spacecraft with real instruments, real mission logic, and real scientific capability, but it sets that mission adrift across timescales that make the whole concept of a planned mission almost meaningless. Nobody who works on the project will live to see results. No institution that existed at launch will exist at arrival. The craft becomes a message in a bottle thrown into an ocean wide enough that the concept of waiting for an answer stops making sense. Parker-class speed gives up slightly less timeline, but changes almost nothing about the fundamental problem. 6,000 years is still longer than all of recorded history, and it is still too long for any shared operational world. The improvement in arithmetic is real, the improvement in practical terms is negligible. Starshot-class speed gives up the timeline problem almost entirely. 20 years is a real planning horizon, a career, a reasonable period for institutional memory to survive. But to achieve that, we give up almost everything we usually mean by spacecraft. The payload drops to gram scale. The mission becomes a flyby by necessity. The propulsion infrastructure balloons to civilizational scale on the ground, and the science window at the far end shrinks to whatever a chip-sized probe can capture during a brief encounter at relativistic speed. Long-shot class thinking restores mission seriousness, real instruments, real science capability, real communication bandwidth, and the timeline immediately expands back toward a century or more. You cannot have everything at once. The ladder makes that constraint perfectly legible, and we should spend a moment on what a century-scale mission actually requires, because the word century can also become abstract. A century is the span of a human lifetime, approximately, and it is 4 to 5 full generations of researchers, and it is the distance between the Wright brothers and routine commercial aviation, and it is roughly the span from the invention of radio to global satellite communication. The world at the end of a century-class mission will be substantially different from the world at its beginning, in technology, in politics, in institutional structure, in the scientific questions that feel most pressing. A 100-year mission is not a slightly longer version of a 10-year mission, and it is a different species of project, one that requires a kind of institutional continuity and cultural patience that human civilization has very rarely demonstrated in scientific or engineering contexts. The longest-running scientific observing programs, some astronomical survey projects, some monitoring networks, hint at what it would require. But they operate on far smaller budgets and far less absolute commitment than an interstellar mission would demand. So the ladder shows us something beyond the travel time numbers themselves. It shows us that there is no version of interstellar travel that avoids hard trade-offs, and there is no combination of speed and payload and mission richness that gives us everything we want at a price we can casually afford. Every rung on the ladder is a negotiation, and the nearest star is where those negotiations become impossible to avoid for the first time. Let's put some substance behind the word advanced propulsion, because it tends to function as a placeholder in conversations about interstellar flight. The propulsion system most often cited as the realistic next step beyond chemical rockets for interstellar applications is nuclear fusion. The idea is not new. Project Daedalus in the 1970s was a serious British Interplanetary Society study of a fusion-powered probe to Barnard's star, a red dwarf about 6 light-years from Earth. The study concluded that a fusion-propelled probe could reach Barnard's star in about 50 years. Now, 50 years is real, and it is within a career, and it is a period across which institutional memory can plausibly survive. But Project Daedalus required a level of fusion engineering that did not exist then and does not exist now. The design assumed inertial confinement fusion using deuterium-helium-3 pellets, a technology that in the 1970s was theoretical and remains deeply challenging today. And it required a spacecraft with a mass on the order of 50,000 tons at launch, mostly propellant, to achieve the necessary exhaust velocities. So the good news is that fusion propulsion could plausibly cut travel times from thousands of years to decades for a serious robotic mission. And that is a real and meaningful improvement in kind, not just degree. The bad news is that we do not yet have fusion power at all in the form needed for propulsion. The pursuit of commercial fusion energy has been ongoing for decades, with genuine recent progress. But the gap between a fusion power plant and a fusion rocket capable of the exhaust velocities Daedalus required is still significant. And even assuming fusion propulsion becomes available, the other constraints do not vanish. Communication delay is unchanged by propulsion advances. It is set by the speed of light, not the speed of the spacecraft. Braking remains a serious challenge unless the propulsion system can be run in reverse. Shielding requirements increase with speed. Payload mass still drives the entire design. So fusion propulsion would be a genuine breakthrough for interstellar capability. It would move some mission classes from fantasy into engineering reach, but it would not dissolve the full stack of constraints that Alpha Centauri represents. And that is the right lesson to carry. Better propulsion is necessary, but it is not sufficient. The nearest star requires progress on multiple fronts simultaneously, and advances in propulsion alone, however welcome, do not simplify the whole problem. They simplify the travel time component while leaving the rest of the architecture still demanding. That question is fussier, and it is also the only one that tells the truth. A flyby and an arrival are not the same class of event. That sounds obvious, but interstellar discussions keep blurring the line, and the blur is not careless, it is seductive. It lets a single promising number carry more weight than the physics actually allows. Now think about what a mission at 20% of light speed is actually doing near the Alpha Centauri system. But it is not drifting in with time to survey targets patiently, and it is racing through. Every instrument has to survive the years of transit, survive whatever particle damage the journey has imposed, point correctly during a brief encounter window, and transmit useful data across 4 light-years afterward. The science happens inside a very tight design corridor. So when we hear that a concept could reach Alpha Centauri in 20 years, the next sentence has to be, reach it as what? As a tiny probe, as a high-speed flyby, as a mission whose definition of success is very different from what we mean when we imagine an orbiter, a long-duration observatory, or anything involving people. And the narrowness of that definition is not a weakness in the concept, it is the source of its honesty. A fast flyby shows us the thinnest possible form of interstellar success that might be achievable on a human planning timescale. The thinness matters because it tells us how much of our ordinary arrival intuition has already been traded away before the mission even launches. Now look at what happens the moment we ask for more. Suppose we want a probe that can slow down inside the system, that it can spend time inspecting multiple targets, that it can adjust its science priorities after first arrival results come in. Immediately we need more mass, more power, more guidance capability, more communication bandwidth, and some mechanism for shedding enormous speed at the far end. The mission class changes entirely, the design burden explodes, and payload sits at the center of all of it. Payload is where dreams become accounting. A larger payload means better instruments, more shielding, stronger communication hardware, more fault tolerance, more onboard intelligence, and more scientific ambition. But payload mass is never free. Every kilogram must be accelerated to interstellar speeds. If it is also meant to slow down at the far end, every kilogram must also be decelerated. so every improvement in what the craft can do at the destination directly worsens the problem of getting it there. And that is why interstellar mission design is so sensitive to how we define success. A tiny flyby probe is the least impossible class because it asks for the least. It does not ask for human survival, orbital operations, a return trip, or much grace after arrival. It asks for one hard burst of usefulness at the moment of closest approach. But our imagination rarely stops there. We imagine missions that inspect worlds in detail, patient observation over weeks and months, orbiters and landers, perhaps one day people. And the moment we imagine those things, speed stops being a simple advantage. A craft arriving at enormous velocity has to shed that velocity to stay. And shedding velocity at interstellar speeds is one of the hardest unsolved problems in this entire field. So this is really about verbs: to cross, to encounter, to arrive, to remain, to return. Public conversation often slides between those as if they were variations on the same task. They are not. They are different species of mission, and the faster the crossing, the more severe that distinction becomes. Now imagine a probe screams through the Alpha Centauri system and detects something unexpected. A target is more interesting than predicted. A planetary atmosphere shows a feature nobody modeled. An instrument underperforms at the critical moment. None of that can be handled with ordinary mission control reflexes, because the craft is not only moving too fast to adjust, and it is also years away in communication time. So even a successful flyby is not just a velocity problem, and it is an autonomy problem, which is what we need to look at next. But before we do, there is one more thing worth saying about the flyby case. New Horizons gave us a stunning first view of Pluto during a high-speed encounter, and even that mission, which crossed the relatively nearby outer solar system, produced an observation window so brief and so geometrically constrained that there are still fundamental questions about Pluto's interior and atmospheric dynamics that a flyby alone could not settle. Now multiply that logic into interstellar distance, add far higher arrival speeds, add years of communication delay, and the severity becomes clear. A fast pass through Alpha Centauri could be scientifically priceless. It could also be the beginning of understanding rather than the end of it. The word there keeps needing correction. A probe can get there in the sense that it enters the system and samples it briefly. A more capable spacecraft gets there in the sense that it can remain and continue observing. A human expedition gets there only if a rival leaves behind a functioning, alive crew with the capacity to do real science in their new environment. Let's go deeper on why the distinction between flyby and arrival matters so much for the actual science. Think about what we have learned from flyby missions inside our own solar system, and then think about what has required orbiters and landers to understand properly. The Voyager flybys of Jupiter, Saturn, Uranus, and Neptune were transformative. They gave us the first close-up views of those worlds and their moons. They discovered volcanoes on Io, complex rings around Saturn, and a striking variety of geological activity across the outer solar system. Every one of those flybys rewrote our understanding of what those systems looked like. But they also left enormous questions unanswered, questions that orbiting spacecraft have since spent years and decades beginning to address. Cassini orbiting Saturn for 13 years revealed how ring structures evolve over time. The Galileo orbiter at Jupiter made repeated passes of the Galilean moons and began to understand the subsurface ocean beneath Europa's ice. New Horizons, despite being a flyby, generated so much data that scientists are still publishing new findings years after the encounter. But there are fundamental questions about Pluto's geology and atmosphere that a flyby geometry could only partially address. Now scale that logic to Alpha Centauri. If we send a fast flyby probe, we get one encounter with each target, one geometry, one narrow slice of time. Whatever the planet looks like at that exact moment is all we get from the direct observation. We cannot return to see how things change. We cannot observe weather patterns across seasons. We cannot identify something interesting and then slow down to look at it more carefully. We race past and take what we can. That can still be scientifically transformative. The first clear images of a planet around another star, especially if it shows signs of an atmosphere or a surface or something we did not predict, would be among the most significant observations in the history of science. A fast flyby could deliver that. But science almost never settles for first impressions. Science follows up. It repeats. It tests different conditions. It asks new questions prompted by the initial answers. And at Alpha Centauri, following up means sending another mission, which means another several decades of transit time at minimum, assuming we have already solved the propulsion problem once. So a flyby to Alpha Centauri is not a finished scientific program. And it is an opening statement, a remarkable one, perhaps. But an opening statement followed by a decades-long silence before the next question can even be asked, and a decelerating orbital mission, the kind that could actually spend time in the system, changes that entirely. It allows repeated observations, changing viewing geometries, follow-up after unexpected discoveries, observation across time, and that is the difference between photographing a city from a passing airplane and living in the city long enough to understand how it works. Now the orbital mission is much harder. We have established that. But the scientific return per mission is vastly higher. And that means the question of mission class is not just a question of engineering feasibility, and it is a question of what kind of science we are actually trying to do. And the two are not always asking the same thing. We have talked about flyby versus arrival at the conceptual level. Let's get more specific about what a genuinely rich arrival at Alpha Centauri would actually need. Picture what we would want from a mission to Proxima b, the planet orbiting in the habitable zone of Proxima Centauri. First, we would want to understand the atmosphere. Is there one? How thick is it? What is it made of? Are there biosignature gases present, oxygen, methane, ozone, at levels inconsistent with purely geological production? That requires spectrographic observation at multiple wavelengths, ideally over multiple orbital periods of the planet, weeks of observation at minimum, possibly months. Second, we would want to understand the surface. Is there liquid water? What is the surface pressure? Are there geological features? What does the day-night terminator region look like if the planet is tidally locked? That requires imaging capability across a range of geometries as the planet rotates around its star. Third, we would want to understand the radiation environment. How does Proxima's flaring affect the planet's atmosphere in real time? Is the magnetosphere strong enough to provide protection? How variable is the space weather? That requires monitoring over extended periods, not a snapshot. And fourth, we would want to understand the wider system. Are there other planets? Is there a debris disk? How does the binary companion system interact gravitationally with Proxima at the distances that matter for planetary stability? None of that can be captured in a brief flyby. Every one of those science goals requires orbital time, multiple revisits, the ability to notice something unexpected and change the observation plan, the patience that comes from being in a system rather than passing through it. And all of that requires, in turn, a spacecraft that can slow down, carry enough power for extended operations, communicate enough data home to justify the mission, and survive long enough in the target environment to accumulate meaningful observations. So when we compare a flyby to an arrival, we are comparing a first glimpse to an actual scientific program. Both are valuable, but they are answering different questions and delivering different kinds of knowledge. And the nearest star matters more as a destination, not just a target. The more seriously we take the second kind, same destination, completely different meanings of success. At Proxima Centauri, a one-way light speed message takes about 4.24 years. A reply takes another 4.24 years. So the shortest possible round-trip exchange between Earth and a probe at Proxima is about 8.5 years. Now let's feel what that actually means, because it's easy to say it and not quite grasp it. Imagine a probe arrives and detects a problem. A camera is slightly misaligned. A radiation event has corrupted part of its navigation software. The observing plan needs to change because a target environment looks different from predictions. The probe sends its status report home. Earth receives it more than 4 years later. Engineers analyze it, debate the options, prepare new instructions, and transmit them back. The probe receives that response more than 4 years after that. One troubleshooting exchange has just consumed nearly a decade, and that changes everything about what mission design even means. Inside the solar system, we still live in a world where mission control feels genuinely present. Delays matter, of course. Mars is not the Moon. Jupiter is not Mars. But the relationship between spacecraft and civilization still feels continuous. Data comes in, humans think, commands go out. The mission remains part of a shared operational time world. Alpha Centauri breaks that continuity entirely, and there is no real-time piloting, and there is no ordinary back and forth, and there is no meaningful sense in which an unexpected event can be handled by a quick human decision from the ground. By the time a message arrives from Earth describing a solution, the immediate situation it was responding to may already be resolved, irreversible, or transformed into a different problem entirely. So autonomy stops being a feature and becomes a condition of existence. A probe at Alpha Centauri has to prioritize its own science agenda, diagnose its own faults, protect itself during critical moments, and make local decisions that no one at home can supervise in time. In that sense, the spacecraft must carry part of mission intelligence within itself. The farther it travels, the more final its own judgment becomes. Now look at how this changes the emotional meaning of the whole enterprise. Travel time tells us the crossing is long. Communication delay tells us the separation is deep in a different and arguably more unsettling way. A destination that takes years for light to reach is not merely far away, and it is out of conversational reach. It cannot be spoken with normally, it cannot be supervised normally, it cannot be rescued in any ordinary sense, and that is already true for robotic missions. For human missions, the effect becomes stranger and more profound. A crew at Alpha Centauri would not just be living far from Earth, they would be living years out of sync with Earth. News from home would arrive stale, advice would arrive late, medical consultation, political decisions, personal grief, technical emergencies, and simple human connection would all be slowed into a rhythm that no civilization has ever treated as ordinary life. Now think about what this does to science operations specifically. Suppose a probe detects something unplanned but valuable, a previously unseen atmospheric event on a planet, a transient signal from the stellar surface, a collision that creates a new debris field. On a normal solar system mission, the discovery triggers rapid analysis on Earth. New observations get requested. Fresh ideas get tested against the unfolding reality. Teams argue over the interpretation in real time and adapt the mission's priorities. At Alpha Centauri, that entire rhythm slows almost beyond recognition. By the time Earth learns the event occurred, it is already years in the past. The machine must notice the surprise, interpret it, and often act on it before any human being has even received the alert. So the mission becomes psychologically strange. The probe is not simply a remote instrument following orders, and it is a delegated intelligence acting in our name inside a place we cannot reach quickly even with thought. And again we meet the same relentless pattern. Solving this problem, building genuine autonomy into the spacecraft, adds mass and complexity. More sophisticated onboard systems mean more ways to fail in unplanned modes. Every improvement has a cost. The distance does not simply ask for patience, it asks the mission to carry pieces of civilization inside the vehicle itself. And for people, the strangeness goes deeper still. A crew heading toward Alpha Centauri would remain culturally connected to Earth in memory, identity and value, but not in tempo. They would leave inside one world and correspond with a different one. Decisions sent home for consultation would return into a moment years in the future. The mission would not just depart from Earth spatially, it would depart from Earth temporally. And that is a kind of separation no human migration has ever had to treat as normal life. We talked about communication delay as an operational problem, but it is also an architectural one. When engineers design spacecraft for solar system missions, they make a set of assumptions about how much human oversight will be available and how quickly it can respond to unexpected situations. For Earth orbit missions, oversight is essentially continuous. For Mars missions, delays of up to about 20 minutes each way mean that certain actions must be automated, but humans can still intervene in most situations on a useful timescale. For outer solar system missions, delays of hours mean the spacecraft must execute many operations autonomously, but humans can still diagnose problems and send corrections within a day. At Alpha Centauri, even the shortest possible response time is more than 4 years. But that is not a quantitative extension of the same design philosophy, and it is a qualitative break. At that lag, the spacecraft cannot be treated as a remote extension of human engineering judgment. It must be treated as a local agent that carries human values and priorities within itself, makes real decisions about what to observe and how to respond to anomalies, and operates according to principles that were defined years before the decisions that require them arose. And that is a profound design challenge. It means the spacecraft has to be preloaded with something like scientific judgment. It cannot simply execute a sequence of pre-planned commands, because the pre-planned sequence may be invalidated by the very discoveries the mission makes. The probe needs to understand its own priorities well enough to adapt them in real time when the actual Alpha Centauri system differs from what was modeled on Earth. We have some experience with lower-level versions of this in space exploration. Mars rovers have become progressively more autonomous in their navigation and target selection. They can identify scientifically interesting rock formations, approach them, and select observations without step-by-step Earth guidance. That autonomy has been essential because even at Mars, communication windows are limited and delays are long enough to make waiting for Earth approval for each action impractical. But Mars rover autonomy is still operating under a framework of regular human oversight and correction. Mistakes can be identified and addressed within days or weeks. A mission at Alpha Centauri would need to operate correctly for years without meaningful human course correction. And this has implications beyond just the technical challenge. It raises questions about what kinds of decisions we are comfortable delegating to a machine for years at a time. If the probe discovers something that could determine whether it should prioritize one target over another, say signs of atmospheric activity on one planet that seem more biologically interesting than another, how should it choose? If a system failure means it must sacrifice some mission objectives to preserve others, which ones take priority? But these are not questions that engineering specifications alone can answer. They require something closer to a codified scientific value system, embedded in software and hardware, trusted to operate in isolation in conditions we could not fully anticipate. And that, ultimately, is one of the deepest reasons Alpha Centauri remains a frontier. Not just because it is far, because the kind of mission that could seriously engage with it would need to carry more of human intelligence and human values within it than anything we have yet built. So when we hear that communication delay is a technical challenge, we should understand it as something larger. And it is a systems problem, a governance problem, a social problem, and a philosophical one. And it is where the nearest star stops being merely far away and starts meaning something structurally different from any other destination humanity has ever pursued. When people imagine a mission to another star, most ask one question first: how fast can we go? That matters enormously, but it hides an equally severe question that tends to show up later, almost as an afterthought. How do we stop? A flyby and an arrival are different mission classes for exactly this reason. A craft carrying enormous interstellar velocity is carrying enormous kinetic energy. If we want to do more than sweep through the system once, if we want to orbit, to observe patiently, to revisit targets, or to make any use at all of a destination after reaching it, that energy has to go somewhere, and the means of removing it almost always add mass, complexity, or dependence on infrastructure that may not exist yet. Now think about why this problem lands so hard at interstellar distances. Inside the solar system, we have developed braking into a sophisticated craft, orbit insertion burns, aerobraking through thin atmospheres, trajectory corrections timed to the exact geometry of planetary gravity fields. And these are genuinely difficult operations, but they happen inside an environment where communication is still measured in minutes or hours, where oversight feels meaningful, where the mission is still connected to a living support structure. At Alpha Centauri, braking arrives after the spacecraft has already spent decades or centuries crossing the interstellar medium. The mission has operated under long communication delay for its entire transit. It has consumed enormous energy simply to reach the speed that makes the crossing tractable, and now it needs to spend comparable energy doing the opposite. The penalty for getting the braking problem wrong is total, and there is no second attempt, and there is no adjustment from the ground. If the system fails at the moment of arrival, the entire mission becomes a very fast flyby that nobody planned for, and the design challenge is almost viciously circular. Carrying onboard propellant to slow down means adding mass at departure. More departure mass makes acceleration harder. Harder acceleration demands more energy or larger propulsion systems. Larger propulsion systems add more mass. The act of solving arrival directly worsens departure. Interstellar design keeps looping back on itself this way, and there is no clean way out of the loop without accepting significant compromise somewhere. Now think about the common shortcut in popular coverage. Most explainers quote an outbound cruise speed, divide distance by speed, and stop there, and that is useful for the simplest travel time benchmark, and it is completely inadequate for any arrival benchmark that matters. A mission that reaches the Alpha Centauri system at extreme speed may technically enter it, but if it cannot slow down, it cannot orbit, cannot inspect targets patiently, cannot change course, cannot choose what to look at next, and that is a different kind of reaching. And this is why many of the serious concepts we looked at in the last chapter favor flybys. A flyby is not a failure of imagination, and it is a disciplined acknowledgement of what physics currently permits. It says we may be able to cross the gap quickly only by giving up the dream of staying. That trade is honest. But the moment we ask for more, for a mission that dwells, that explores, that remains present inside the system, the braking problem returns at full force. People have proposed various approaches to this. Magnetic sails that use the interstellar medium to generate drag. Light sails using the destination star's own photons as a brake. Multi-stage vehicles that shed their propulsion system after acceleration and use a separate system for deceleration. External infrastructure that meets the probe at the far end. Each idea is genuinely interesting. Each also comes with severe requirements in geometry, timing, mass budget, or civilizational commitment. None of them makes braking casual, and for a crewed mission, the difficulty becomes far harsher still. A human ship cannot count a rapid pass through the system as a success in any meaningful sense. If people are meant to arrive alive, healthy, and capable, then the craft must slow in a way that preserves habitat integrity, life support continuity, crew health, and mission usefulness. That means more mass exactly where the design can least afford it. So deceleration becomes one of the cleanest honesty tests in this whole subject. It asks whether we are really talking about reaching another star, or merely about crossing its coordinates at extraordinary speed. The answer matters. The two things are not the same, and here is the final thing deceleration teaches us. Human intuition loves outbound motion. We picture a launch, a cruise, a destination. We naturally give emotional weight to the departure. Physics gives equal weight to arrival. A mission can win the race and lose the destination. Now there is one braking concept worth examining more closely, because it illustrates just how elegantly difficult the problem is. If the probe is using a laser-driven light sail to accelerate during the first half of the journey, could we use the destination star, Alpha Centauri itself, as a braking source during the second half? The idea is that the probe unfurls its sail as it approaches the target system. Instead of receiving a push from the rear, it receives a push from the front, from the light of the Alpha Centauri stars, which acts as a brake. The physics is real. Light exerts radiation pressure. A large enough sail could, in principle, decelerate a sufficiently light probe using stellar radiation. But look at the requirements. The probe is traveling at, say, 20% of the speed of light. The radiation pressure from the Alpha Centauri stars is real but extraordinarily gentle, by the standards needed to decelerate something moving at that speed within a reasonable distance. The deceleration is so gradual that the probe would need to begin braking a very long distance before the target system, potentially before it even entered the system. And the sail geometry would have to be maintained correctly throughout. Maintaining sail geometry during deceleration while traveling at relativistic speed in a particle environment that has been battering the sail for years of transit. That alone is an engineering challenge of remarkable depth. And it has to work using a mechanism with no moving parts and no ability to receive real-time corrections from Earth. But it is not impossible, and it is one of the more creative approaches to the braking problem, and it deserves serious study, but it illustrates the fundamental difficulty elegantly. The only energy source available at the destination is starlight, the very same kind of energy we used to accelerate the probe in the first place, just coming from the other direction, and that energy is enough to push a paper-thin sail a tiny bit, not enough to bring a significant payload to a halt quickly. So even the most elegant proposed solution requires the probe to be extraordinarily light, and it has to have maintained sail integrity across years of interstellar transit, with the geometry and timing exactly right as it enters the target system, all without any real-time guidance from Earth. And the moment we want to do anything more than that, carry heavier payloads, slow down more quickly, orbit rather than flyby, the elegant solution becomes inadequate. We are back to the circular problem. More propellant means more mass, and more mass makes everything harder. And that is why the hidden killer is hidden. Not because it is obscure, because our language of travel keeps privileging the beginning of the journey over its end. It is easy to imagine the space between the stars as a clean, empty corridor. Almost nothing there, a long black passage. Solve propulsion, and the rest is patience. But that picture only holds when the speed is low enough. At high fractions of the speed of light, the emptiness begins to change character. Not because interstellar space becomes dense in any everyday sense. It remains extraordinarily sparse, a near-perfect vacuum by laboratory standards. But sparse is not the same as harmless when the relative velocity is extreme. A dust grain smaller than a human hair can carry the energy of a rifle bullet when your spacecraft is approaching it at a meaningful fraction of light speed. A thin dispersal of hydrogen atoms becomes an erosive environment when you are moving fast enough. The faster the craft moves, the less forgiving the path becomes. And we should be specific about the threats. The interstellar medium contains interstellar dust, tiny particles of silicates, carbon compounds, and metal-bearing grains distributed at very low density throughout the space between stars. It also contains gas, mostly hydrogen and helium, along with heavier elements in trace amounts. It contains high-energy cosmic ray particles originating from supernovae and other energetic events. And it contains the faint remnant magnetic fields threading the galaxy. Under normal circumstances, none of these are a concern. Our solar system plows through the interstellar medium constantly. Planetary atmospheres and magnetospheres absorb what arrives. A fast interstellar probe has no such protection by default, and this is where the design problems become interconnected in an uncomfortable way. A tiny probe can be accelerated more efficiently. Less mass means the laser or propulsion system can push harder for longer. But the same tiny probe has almost no spare mass for shielding. Add protection, and the mass budget shrinks and acceleration becomes harder. Keep the mass low, and the particle environment becomes more dangerous. So the interstellar medium is not a secondary detail. It connects directly back into the propulsion math. Now use a familiar analogy to feel the principle. Water feels soft until impact speed makes it as hard as concrete. Air feels thin and harmless until re-entry turns it into a furnace around a descending capsule. The material has not changed. The interaction has. Interstellar space works the same way. The medium is genuinely sparse. At speeds approaching a meaningful fraction of light speed, sparse is enough. That change forces a set of design questions that do not arise for solar system missions at all. What geometry should the forward face of the vehicle present? How much cumulative erosion is acceptable over years or decades of transit? Where should the most sensitive instruments be positioned relative to the direction of travel? How much additional mass for shielding can the vehicle carry before the concept collapses under its own budget? But these are not decorative engineering details. They are part of the central physical reality. Interstellar travel is not ordinary deep space stretched further, and it is a different damage regime, with different design constraints, different failure modes, and different philosophical implications for what kinds of vehicles can survive the crossing, and the trade-off is relentless. The lower the speed, and particle impacts become less severe, but the travel time grows, adding its own set of problems. Raise the speed, and the travel time falls, but the particle environment becomes harsher. Add shielding, and acceleration worsens. Strip shielding, and survival worsens. Redesign for a smaller cross-section, and the mission architecture changes. Every move pushes the problem somewhere else. Now imagine a crewed ship under the same logic. A human vehicle would have far more cross-sectional area than any probe concept. It would have far more systems that must remain intact throughout the crossing. And it would have far more reasons not to accept cumulative damage, because equipment failures in a crewed ship are not just mission failures, they are threats to the people on board. Even if a crewed mission moved at slower speeds than the most aggressive probe concepts, the crossing would still be a long exposure through an environment that remains subtly hostile at the scale of time, and that leads to a larger correction in how we should picture the mission. We should stop imagining one heroic vehicle sliding through benign darkness. The farther we follow the physics, the more the mission begins to look like an arrangement of compromises, with protection and infrastructure built into every layer. The spacecraft is only the visible tip. The problem is distributed through materials, geometry, propulsion, mission duration, and vehicle mass in a way that resists any simple solution. And the path between the stars already resists simplification. One thing worth adding to the picture of the interstellar medium is that it is not uniform. The space between the stars is not a single homogeneous environment. It has structure at multiple scales, and there are warm, diffuse regions with lower density, and there are denser clouds of gas and dust, and there are sheets and filaments shaped by supernova shockwaves and stellar winds. And our solar system itself sits inside a region called the local bubble, a roughly spherical volume of hot, relatively sparse interstellar gas about 1,000 light-years across, created by ancient supernova explosions in this part of the galaxy. The path from the Sun to Alpha Centauri passes through our local stellar neighborhood inside the local bubble, and on that scale the interstellar medium is relatively benign. The average density of hydrogen atoms is very low, far lower than we would find in denser molecular clouds elsewhere in the galaxy. But even this relatively benign environment matters at the speeds a serious interstellar probe would require, and the structure of the medium along the route is not perfectly known. There may be local variations, denser clumps, higher dust concentrations in small regions, that would affect particle damage rates along the specific path. For solar system probes, we can model and correct for most environmental hazards in real time. For an interstellar probe traveling at high speed, the environment ahead is only partially characterized, and the probe has to be designed to survive the realistic range of conditions it might encounter rather than the average modeled condition. This adds another layer to the design uncertainty. Not a crippling layer by itself, but one more reason why robust engineering margins matter more for an interstellar mission than for any mission inside our better characterized solar system environment. But it is not a blank stage waiting for a vehicle, and it is part of the mission. The road itself has conditions, even if those conditions are almost invisible to ordinary human senses. Here is a sentence that might be the most important practical lesson in this whole video. The mission is bigger than the vehicle. Not metaphorically bigger, physically bigger. In terms of the total system of infrastructure, energy, continuity, and civilizational commitment that any serious interstellar attempt would require, think about what breakthrough starshot actually implies. The probe is gram scale. The sail is a thin membrane. The onboard systems are minimal by any mission standard. But the infrastructure behind the launch is not minimal at all. We are talking about a laser array capable of delivering gigawatts of focused power, a ground-based system that would be among the largest and most energy-intensive precision engineering projects ever attempted. Arrays of lasers synchronized to act as a coherent beam, optical systems larger than anything currently built, a power infrastructure that dwarfs almost any current scientific facility. So the visible part of the mission, the tiny probe sailing outward, is only the final expression of an enormous ground-based system. And that system requires resources, manufacturing precision, and operational continuity that no single nation currently maintains as a routine capability. Now step back from that one concept and look at the pattern it represents. Every interstellar mission concept at the serious level implies background systems disproportionately large compared to the spacecraft itself. Fusion-powered probes require a mature fusion technology we do not yet have. Antimatter drives require production and storage of antimatter at scales orders of magnitude beyond current capability. Laser sails require gigantic beam infrastructure, and all of them require communication relay networks, tracking stations, data reception systems, and institutional continuity lasting decades or centuries. So when we ask whether we can get to Alpha Centauri, the question quickly becomes, what kind of civilization would be required to make that credible? And that is not a dismissal. And that is a real engineering question. It changes the scale of what we mean by mission. Within the solar system, a project can feel self-contained. Its energy use is modest by global standards. Its support structure is demanding but recognizable. The people who build it can imagine the people who complete it. An interstellar mission cannot make those assumptions easily. A probe launched today might return its most important data to people who were not yet born when the design decisions were made. The receiving antennas have to remain operational for decades. The calibration knowledge has to remain legible across generations of engineers. The software has to remain interpretable by people working in a technical culture that may have changed enormously. And the institutional will to keep listening, to keep caring about a signal arriving from a probe nobody alive remembers launching, has to survive in a world where other priorities are constantly competing for attention. That receiving problem is easy to underrate because it does not look cinematic, but a probe can be perfectly designed and still become scientifically mute if the culture waiting for its data loses the continuity to understand what arrives. Now let's also think about what this means for autonomy in a different sense. We have talked about the probe needing to make local decisions at the destination because communication delay makes real-time control impossible. But there is a second autonomy problem that lives back on Earth. A mission that takes decades or centuries to complete has to remain a priority across political cycles, funding environments, institutional reshufflings, and generational turnover. The people who pushed hardest for the mission in its early years will not be the people who receive its results. The scientific questions that seemed most pressing at launch may not be the questions the next generation considers most important. The very framing of the mission, what counts as success, what the data means, who has the authority to interpret it, may shift across the mission's lifetime. So interstellar projects are not only engineering challenges, they are cultural challenges, stewardship challenges. They ask whether a civilization can maintain coherent purpose across timescales longer than any individual career, or any government, or possibly any single institution. When we say an interstellar mission requires civilizational continuity, it is worth being concrete about what that phrase actually demands. Now consider the technical knowledge chain. A spacecraft launched today uses materials, manufacturing processes, software architectures, and engineering standards built up over decades. The people who designed those systems understand them in ways that go beyond what any document can fully capture. They know the failure modes, they know the workarounds, they know what assumptions were made and why. When those engineers retire or die, their successors inherit documentation. Good documentation if the project management was rigorous. But documentation is not complete knowledge. Any large engineering project accumulates contextual expertise that lives in the heads of the people who built it. For a solar system mission, this is manageable. A project running for 20 years can maintain a living institutional memory across that period. People overlap. Knowledge transfers. A project running for a century is harder. A project running for 2 centuries, the outer edge of some interstellar concepts, faces a knowledge continuity problem that has no good precedent in engineering history. Software is especially fragile in this regard. A spacecraft built in 2040 will be running software on hardware that will be obsolete by 2060, completely unrecognizable by 2080, and potentially incomprehensible by 2140. Languages change, architectures change, the entire conceptual framework for how software is written and understood evolves. The probe has to carry software robust enough to survive not just particle damage, but the aging of the technical culture that created it. And the receiving infrastructure on Earth faces similar challenges. The antennas that listen for the probe's signal, the software that processes the data, the scientific community that interprets the results. All of these have to be maintained across the mission's lifetime. They cannot just be built and left running. They require active maintenance, active funding, and active human decision-making about whether to keep investing in a project that may not return its most important data for decades or centuries. So civilizational continuity is not a vague wish, and it is a specific engineering requirement with a specific answer. The mission needs institutions that can sustain technical and scientific coherence across timescales longer than any current human institution has demonstrated the ability to maintain. That does not mean it is impossible, but it means the challenge is not only about propulsion, shielding, and communication, and it is about whether the civilization that launches the mission can hold together long enough to receive what it sent. We said the mission is bigger than the spacecraft. Let's go one level deeper on that. The breakthrough starshot concept, in its most fully articulated form, imagines a laser array built somewhere on Earth, or perhaps ultimately in space, capable of delivering roughly 100 gigawatts of focused laser power onto a departing sail. 100 gigawatts is roughly the total electricity generating capacity of the United Kingdom at any given moment, but that is not a laser you build in a laboratory or even a large facility. And that is a laser you build as a national or international infrastructure project. And it is not a one-time construction effort. It requires ongoing operation, maintenance, calibration, and power supply for as long as missions are being launched. Now imagine building that and then waiting. The probe departs. 20 years pass. The signal from Alpha Centauri arrives. By that point, the people who built the laser array have likely retired. The organization that funded it may have changed its priorities. The political and institutional landscape has shifted. And yet the receiving infrastructure, the antennas, the data pipelines, the scientific teams, has to be maintained, capable, and ready. But that is not a question of engineering capability alone, and it is a question of political will and social memory across 20+ years for a project that produces no intermediate results. The funding agency cannot point to scientific discoveries along the way. The politicians who voted for the budget will not be in office when the returns arrive. The public that was excited at launch will have lived through 2 decades of other events. Science has managed this in smaller ways. The Voyager program has maintained contact with its spacecraft for nearly 50 years. Some long baseline astronomical surveys have run for decades. Large physics experiments like the Large Hadron Collider operate on timescales of decades with sustained international commitment. But those examples all deliver intermediate results. Voyager data comes back continuously, the LHC produces new particle collisions every day, an interstellar probe in transit produces nothing during the crossing, and it is a long bet with no interim dividends. And that is why the mission is not just a spacecraft and a laser, and it is a social contract, an agreement among people who may never know each other, across time spans longer than political cycles, to keep caring about a project whose payoff is delayed in ways that no human ambition has ever had to accept quite this literally. Alpha Centauri makes that requirement visible, and making it visible is one of the most useful things the nearest star does. And that is another reason Alpha Centauri is such a powerful benchmark. It makes that requirement visible at the minimum possible distance. If even the nearest star requires this degree of civilizational depth, then the challenge of interstellar reach is not mainly about better rockets. And it is about whether we can organize sustained purpose across time at a scale we have never quite managed before. The least impossible interstellar mission is a robotic flyby probe. That sentence sounds modest, and it is also clarifying. A robotic flyby probe asks for the fewest miracles. No life support, no return trip, no crew health, no rescue, no habitat, no need to preserve human psychology across decades. The craft can be tiny, the mission can be explicitly one way. Communication delay is severe, but the machine does not suffer loneliness in any meaningful sense. Among all interstellar mission classes, this is the one closest to something we can describe without pretending the rest of the problem has disappeared. Now step up one level. A robotic decelerating probe is substantially harder. The moment we ask the craft to slow down and spend time inside the target system, the braking problem takes over. Mass grows. The mission architecture becomes far less forgiving. Communication delay remains severe. The chance of a rich scientific return improves meaningfully, but the distance between concept and execution widens at the same time. Step up again to a human one-way mission. This sounds at first like a simplification. No return required. Surely that removes a layer of difficulty. And in one narrow sense it does. Return propulsion is not part of the design, and that is a real reduction. But it removes only one line item while leaving all the others intact. Human shielding is still required. Life support across years or decades of transit is still required. Medical capability is still required. Habitat reliability is still required. Social stability across a closed community living in profound isolation is still required. And if the crew is meant to arrive alive and capable of doing science, deceleration is still required. A one-way mission is not a shortcut to plausibility, and it is the same burden with one component removed. Now imagine a human survivable arrival mission in earnest. The spacecraft becomes not merely a vehicle, but an environment. Radiation protection must function reliably for the entire transit duration. Closed-loop life support systems must remain stable without the possibility of resupply. Maintenance must happen locally without external expertise. Serious medical events must be handled with whatever is on board. Governance has to function under conditions of prolonged isolation with no recourse to outside authority. And if the mission is long enough, which it almost certainly will be, culture on board becomes an engineering variable in a way that no current mission has to take seriously. The ship becomes less like a vessel and more like a self-contained society. And then there is the return mission. A human return-capable mission to Alpha Centauri belongs at present outside grounded near-term engineering in any recognizable sense, not because the idea is categorically forbidden, but because the stack of requirements becomes enormous. First, the outbound crossing, then long-duration survival en route, then deceleration at the destination, then the capacity to operate meaningfully inside the system. Then the whole burden repeats for the return. Every stage assumes a civilization willing to sustain the mission through each of those phases, and that civilization has to remain coherent and committed across a timescale measured in human generations. Now watch what happens in public conversations about this. A fast probe concept gets discussed. The audience mentally upgrades it into evidence that crude interstellar travel is advancing in the same direction. But that leap is exactly what the physics does not permit. A gram-scale flyby probe tells us something real about one narrow mission class. It tells us almost nothing useful about a crude mission that must protect living bodies, keep them functioning, and still arrive under enough control to do real work. Probe logic and human logic are not points on a smooth progression. They diverge sharply. A tiny wafer-scale probe and a crude ship do not differ simply by mass. They differ by category. Once life support enters the picture, the architecture changes. Medicine changes it again. Shielding changes it again. The ethical weight of human lives changes everything it touches. And the ethical dimension deserves to be said plainly. A robotic mission can accept one-way sacrifice because a machine has no interior life to betray. Human missions do not have that freedom. The moment people enter the story, every simplification carries moral cost. No return is not just a technical shortcut. Extreme autonomy is not just a systems preference. Generation-spanning transit is not just a schedule note. Uncertain arrival conditions are not just a risk item in the margin. They are decisions about what kinds of human futures are permissible. Let's stay with the human mission question for a moment longer, because it has a dimension that deserves more careful attention. The standard framing treats crude interstellar travel as a harder version of crude planetary travel. More life support, longer duration, more radiation, harder re-entry. The same challenges, scaled up, but there is a dimension that does not scale linearly at all. And that is the question of what kind of human life is being proposed. A crew en route to Alpha Centauri would spend years, possibly decades, in a vessel with no possibility of return, no meaningful contact with the larger civilization that launched them, no access to emergency support, no ability to leave or change their minds once beyond a certain distance, and no guarantee of what they will find at the end. People have endured extraordinary conditions in the history of exploration: long sea voyages in uncertain conditions, Antarctic expeditions that lasted years. The first astronauts accepted risks we would now consider extraordinary. Human beings can demonstrate remarkable adaptability when the goal feels important enough, but none of those situations combined all of the features of an interstellar mission simultaneously. Even the most isolated historical explorations could send messages home and receive replies within weeks or months. Even the most dangerous expeditions could be recalled or resupplied in principle. The psychological and social architecture of isolation at the scale of an interstellar voyage is genuinely unprecedented. And then there is the question of informed consent over time. People who volunteer for an interstellar mission sign up with a certain understanding of conditions, but the conditions over decades may diverge from anything they could have anticipated. Medical emergencies that were not predicted, social tensions that were not modeled, technical failures that require abandoning parts of the mission plan. The crew makes ongoing decisions, some of them consequential and irreversible, in a context of isolation that makes ordinary oversight impossible. Who has the authority to make those decisions? The crew itself. But the crew was selected, trained and briefed by a civilization that they are now years away from in every practical sense. The mission's original purposes and the crew's evolving priorities may diverge. Who is right? But these are not hypothetical philosophical puzzles. They are real design problems. An interstellar mission architecture has to have answers, codified, tested, as robust as possible, to questions about decision authority, dispute resolution, and what happens when crew consensus breaks down in a situation that Earth cannot address in time. So a crewed interstellar mission is not just a bigger spacecraft. And it is a floating governance problem. A social contract written in advance for a community of people who will face situations nobody could fully anticipate, in a place where the original contract writers cannot intervene. And that is why the gap between probe logic and human logic is not merely a difference in mass and life support. And it is a difference in the kind of challenge being posed. A probe asks, can we build a machine robust enough? A crewed mission asks, can we design a civilization robust enough? Alpha Centauri does not forbid the answer to be yes, but it demands that we be honest about the question. So Alpha Centauri should not be used casually as a symbol of human destiny. For probes, the language of experimentation makes sense. For people, the language has to become far more careful. A crewed mission to the nearest star would not just test propulsion and shielding. It would test the ethics of sending human beings into a condition of deep separation that no civilization has ever tried to normalize. And that is a much bigger threshold than the phrase nearest star suggests. Alpha Centauri is important because it is ordinary by interstellar standards, and that is the part worth holding on to most carefully. The system is nearby, and it is famous. It tempts the imagination. It has planets. It has named stars and a rich observational history. But its deepest scientific value as a test case is that it is the best case example of the interstellar problem. If any star system were going to be cooperative with our travel ambitions, this one would be. It gives every optimistic argument its most favorable starting point, and it is the minimum interstellar challenge that nature offers. And even here the barriers stack up fast. Distance alone is enough to turn present-day spacecraft into epoch-spanning messengers. Communication delay is enough to break ordinary mission control. High speed turns the interstellar medium into a design threat. Meaningful arrival demands braking that may exceed our current engineering reach. Useful payloads demand mass that worsens everything. Human missions demand whole new layers of survivability and ethics. External infrastructure must grow to civilizational scale. Institutional continuity must extend across generations. The more honest the mission description becomes, the less the phrase nearest star can comfort us. Now notice what that does to our picture of the galaxy. Popular imagination often makes the stars feel like a wider version of the solar system. Spread out, yes. Harder, yes. But still loosely scattered destinations waiting for patient expansion. Alpha Centauri is the cleanest argument against that picture. If the gentlest possible interstellar crossing already behaves like a systems-level barrier, then the stars are not arranged for ordinary travel. They are isolated by a change of regime. That does not mean forever impossible. It means something more disciplined than that. It means interstellar travel is not the next obvious step after Mars becomes familiar. But it is not what happens when the rockets get faster and the engineers get more confident. It belongs to another layer of technological and civilizational commitment, one that we have not yet demonstrated we can sustain at the required scale. And here is where Alpha Centauri changes the meaning of our ambitions. Within the solar system, we can still imagine increasing traffic, shared infrastructure linking planets and moons, dense communications, a growing civilization that expands gradually from one world to another inside a connected system. Between stars, even if travel becomes possible one day, the communication delay alone means tightly networked interstellar societies are much harder to imagine than tightly networked interplanetary ones. Stellar civilizations, if they ever exist, may be far more locally autonomous and far more temporally separate than planets within a single system. The barrier is not only travel, and it is coordination. Two civilizations at different stars cannot share a common present in any meaningful operational sense. They can share information slowly, over years. They cannot make decisions together, and that is one reason why the nearest star is so intellectually powerful as a documentary subject. But it is not just a propulsion problem, and it is a window into the fundamental structure of the universe we inhabit. We live in star-centered basins of energy and time. Crossing from one basin to another is not impossible in principle, but it is intrinsically hard in a way that does not go away with better technology alone. The separation is structural. Now compare that with how Alpha Centauri feels in the sky. It can sound intimate because it has a name, because it is famous, because it is the closest, because star maps make the local stellar neighborhood look compact. It almost seems as if the universe is offering one neighboring shore, close enough to row toward with enough determination. But the physics says otherwise. The nearest shore is already separated by years of light travel, thousands of years at any spacecraft speed we currently know how to achieve, severe communication lag, difficult braking, and a payload trade-off that punishes every attempt to turn a fast crossing into a rich arrival. And that is the real payoff of this video. Alpha Centauri is not powerful because it is a dramatic exception to how we imagine the cosmos. And it is powerful because it is merciful, the gentlest case available, and it is still severe. It gives the universe every chance to seem reachable, and then it defeats the mental shortcuts we keep bringing to it. One thing we have not said explicitly, and should say, is that physical travel to Alpha Centauri is not the only way to learn about it. Remote observation has already transformed our understanding of the system dramatically. Spectrographic analysis of the star's compositions, radial velocity measurements hunting for planetary signatures, direct imaging programs searching for companions, astrometric measurements tracking proper motion, atmospheric modeling based on stellar properties. All of this has been done and is being done from telescopes on Earth and in orbit. Webb has opened new windows for studying exoplanet atmospheres, including around nearby red dwarf systems. The Habitable Worlds Observatory, proposed as the next major NASA flagship telescope after Roman, is specifically designed to directly image Earth-like planets around nearby stars, including Alpha Centauri. That mission, if funded and launched in the 2030s or 2040s, could give us direct images of any planets in the habitable zones of the Alpha Centauri system, and potentially even spectroscopic information about their atmospheres. That would be a staggering scientific result. It would not be the same as sending a probe, but it would be achievable within a realistic near-term timeframe, at costs orders of magnitude lower than any serious interstellar mission, and it would dramatically sharpen the science case for whatever physical mission eventually follows. And this is an important corrective to the framing that treats remote observation and physical missions as alternatives or rivals. They are not, they are sequential. Remote observation from improving telescopes is probably the realistic near-term way to learn about Alpha Centauri. Physical missions, first tiny probes, then eventually something richer, are the long-term program that builds on what remote observation reveals. So when we say that Alpha Centauri is hard to reach, we do not mean it is hard to learn about. We mean that physical contact carries costs that remote observation does not. And those costs have to be justified by science goals that remote observation alone cannot achieve. Understanding what those goals are, what specifically you would need a probe for that a telescope cannot provide, is itself an important scientific question, and answering it rigorously will help focus the case for interstellar missions when the technology eventually catches up. And there is one more dimension of what Alpha Centauri reveals about the stars, and it is worth naming even if it opens a larger question than we can resolve tonight. The Fermi paradox asks, if intelligent life is common in the universe, why have we found no evidence of it? The universe is billions of years old. Life has had enormous time to develop, spread, and make its presence detectable across galactic distances. Alpha Centauri gives us a small piece of that question's answer. If reaching even the nearest star system is as hard as we have spent this video demonstrating, if it requires decades or centuries at minimum even for the simplest probe class, if it demands civilizational infrastructure and sustained commitment at extraordinary scale, if it imposes communication delays that break ordinary forms of social organization, then the stars are naturally isolated. They are not isolated because intelligence is rare. They may be isolated because the physics of interstellar crossing is intrinsically hard for any civilization, no matter how advanced. A civilization that developed on a planet around one star faces the same communication delays, the same travel times, the same braking challenges, the same particle environment that we face. The speed of light is the same everywhere. The distances between stars are what they are. An advanced civilization may solve the engineering problems we cannot yet solve, but it still has to work within a universe where even its fastest messages take years to travel between stars, and where physical travel requires energy and time commitments that impose real limits on any program of expansion. So Alpha Centauri is not just a destination, and it is a window into the structure of the universe at the scale that matters for any technological civilization's prospects for contact with others. If expansion is slow and contact is rare because the physics is genuinely hard, then the night sky's silence is less mysterious than it first appears. It may simply be what physics predicts. That does not mean we are alone. It means we should not expect the universe to have organized itself for easy interstellar connection. The stars are isolated in ways that may limit even advanced civilizations, and Alpha Centauri is the closest place to see that principle at work. That defeat is not defeat in the sense of failure, and it is defeat in the sense of correction. It removes a false picture and puts a truer one in its place. And a truer picture, even when it is harder, is worth more than a comfortable one. By the time we have followed Alpha Centauri all the way through, the answer is much cleaner than when we began. The nearest star system feels close only if we compare it with the galaxy. The moment we compare it with real missions, real payloads, real communication constraints, and the real requirements of human survival, that feeling collapses. And the collapse is useful. It tells us something true about the universe we actually inhabit. Interstellar space is not an extension of ordinary deep space, and it is a different regime of reality. And the difference is not merely one of bigger numbers, and it is the way the numbers recruit each other into a compounding system of constraints. Distance recruits travel time recruits autonomy, speed recruits shielding, arrival recruits braking, payload recruits energy, human presence recruits an entire world of survival problems that robotic missions do not face, and none of those constraints can be solved in isolation, because solving one tends to worsen another. So we can finally answer the question from the opening in the most honest form available. If Alpha Centauri is the nearest star system, why does reaching it still break almost every mission idea we know how to imagine? Because nearest does not measure what matters most for travel. It does not measure travel time at speeds we can actually achieve. It does not measure the years-long lag that separates any probe at that distance from any oversight at home. It does not measure the cost of slowing down enough to do real science in the target system. It does not measure the mass penalty for useful payloads. It does not measure the difficulty of keeping hardware intact and functional across decades or centuries. And it does not measure the burden, physical, psychological, ethical, of keeping people alive beyond any rescue, in a place where home is a 4-year-old echo and not a present voice. And here is the deeper lesson that all of that adds up to. If the easiest possible star is still this demanding, then the real story of the stellar neighborhood is not that it is waiting just beyond our current engines. The real story is that solar systems are profoundly isolated from one another in practical terms. Not in a way that forbids every future ambition, but in a way that requires us to think at a scale we have not yet demonstrated we can sustain. That conclusion is not meant to flatten the dream. It does not tell us what a mature technological civilization might eventually attempt. It tells us what the honest starting map has to look like. Serious ambition begins with honest scale, and the nearest star is where that scale first becomes impossible to ignore. Now think about what that benchmark gives us. Alpha Centauri is not powerful because it is uniquely dramatic, and it is powerful because it is the mildest interstellar case nature offers, and still severe. Every optimistic claim about interstellar travel has to survive contact with this benchmark first. If a concept cannot account for what the nearest star requires, it is probably not describing the future, and it is describing a wish dressed in engineering language. And there is a cultural shift that comes with taking the benchmark seriously. Alpha Centauri reduces one kind of arrogance while deepening another kind of ambition. It reduces the arrogance that assumes technological progress automatically entitles us to every horizon on the same terms we used to reach the last one. A civilization can become extraordinarily capable and still find the stars stubbornly separate. But it deepens ambition by clarifying what would be required to actually bridge that separation. More patience than any project has ever demanded, more precision in both engineering and intention, more infrastructure-heavy thinking than has ever been applied to exploration, more willingness to think across generations rather than quarters or even decades, more honesty about trade-offs. Let's close by making the benchmark argument as concrete as possible. Any claim about the future of interstellar travel can be tested against Alpha Centauri in a straightforward way. You take the claim, apply it to the nearest star with its known distance and known physical properties, and ask, what exactly does this change? If the answer is specific, this propulsion advance reduces the transit time for a gram-scale probe from 2,000 years to 40 years under these specific assumptions. The claim is making contact with the physical problem, and it is telling us something real. If the answer is vague, this breakthrough will bring the stars within reach. The claim has not yet made contact with the physical problem, and it is expressing a hope or a feeling, not a result. And that distinction matters enormously for how we allocate scientific attention and funding. Specific claims about specific mission classes can be evaluated, challenged, improved, and built upon. Vague claims about eventual possibility cannot. They can only be repeated with varying levels of enthusiasm. Alpha Centauri forces specificity because it has a definite distance. It has definite physical properties. It has a definite set of constraints that any proposed mission must address. A concept that cannot answer what it would actually do about communication delay, or braking, or payload mass, or institutional continuity, is not yet a concept in any meaningful engineering sense. And it is a direction of imagination, and directions of imagination are valuable. They are where everything begins, but they have to become something more rigorous before they are worth treating as predictions or programs. So the benchmark is not a test designed to make ideas fail, and it is a test designed to see which ideas are ready to advance. And that is a necessary function in a field where the emotional stakes, the deep human desire to reach other stars, can easily outpace the technical reality for years or decades at a time. Alpha Centauri gives us a standard that does not move with the enthusiasm of the moment. and it is fixed by physics, and it is clarified by our best measurements. And it is the same challenge whether we approach it with optimism or skepticism, and that stability is exactly what makes it valuable. The nearest star is honest in a way that human ambition often is not, and that honesty is not a limitation, and it is a gift. Alpha Centauri is close enough to force that self-portrait into focus, and in forcing it, it becomes one of the most valuable objects in astronomy, not because we can easily reach it, but because we cannot. So where does Alpha Centauri leave us? Not with despair, not with vague optimism either, with something more useful than both. The nearest star does not tell us the stars are unreachable in every imaginable future. It tells us that the dream of reaching them lives in a harsher physical world than our language first admits, and that distinction matters. And here is a final thought that belongs in this video, and it is about the relationship between difficulty and meaning. Human beings are not well calibrated for projects that unfold across generations. Our planning horizons are biological. A career is a few decades. A political cycle is a few years. Even a large infrastructure project, a dam, a railway, a city, usually delivers results within a century. We can maintain some institutions across longer periods, but maintaining them in a state of active, purposeful effort, rather than passive, bureaucratic inertia, is genuinely hard. Alpha Centauri asks for something beyond what we have demonstrated we can sustain. A mission that takes 20 years to arrive and requires decades more of scientific follow-up is not unusual by the standard of human experience. A mission that takes a century asks us to plan beyond a single career. A mission that takes millennia is so far beyond ordinary institutional thinking that it belongs to a different category of ambition entirely. And yet the universe does not care about those timescales. The stars will be where they are regardless of whether we find them convenient. The barriers to reaching them are set by physics, not by our preferences. So what does it mean to take the nearest star seriously in the face of that? It means being honest about what we are and are not ready to attempt. It means not pretending that enthusiasm is engineering. It means building the foundational capabilities, better telescopes, better communication systems, better propulsion research, better autonomous software, that will eventually make the simplest missions credible. It means doing the science and mission analysis that clarifies what a probe would actually find and why it would be worth the effort. And it means maintaining the habit of measuring ambition against reality, rather than letting ambition define reality. The nearest star earns every year we spend thinking about it carefully. It does not reward shortcuts. It does not flatten to optimistic headlines. It stays exactly as hard as the physics says it is, and that is a better kind of teacher than the universe had to be. The nearest star is the most honest benchmark we have, and honesty in the long run is what makes the dream worth having. We began with a number, 4 light years, small enough to say in one syllable, familiar enough to hear without fear, close enough in stellar terms to feel like the first natural step. And then we followed each layer of what that number actually means. The distance is not a journey we can extend from current practice, and it is a regime change, a place where mission problems stop scaling gracefully and start requiring entirely new frameworks. Travel time at any speed we currently command stretches from decades into millennia. Communication delay cuts the mission off from ordinary oversight and demands that the spacecraft become partly self-governing. Speed introduces particle damage that cannot be ignored. Meaningful arrival requires braking we have not solved. Useful payloads make every other problem harder. And human presence, if we ever want to talk about it honestly, adds layers of ethical and physical complexity that a probe does not have to carry. None of that adds up to impossible, but all of it adds up to a boundary, a real one. Not a temporary limit that faster engines will casually dissolve, but a structural feature of how the universe is arranged. Stars are separated by more than distance. They are separated by a change in category, from the solar system, where civilization can remain continuous and present, to the interstellar regime, where even light arrives late and nothing stays connected in real time. And Alpha Centauri is where we first meet that boundary clearly. Not at some extreme distance, not in a hypothetical scenario involving travel to the galactic core. Right here, at the nearest possible case, with the most favorable geometry the universe offers us. And that is why this star system matters beyond its scientific content. And it is the benchmark, and it is the place where any claim about the future of human exploration has to prove itself. If a concept cannot account for what the nearest star demands, it is describing something other than the physical universe, and there is a quiet gift in that. Alpha Centauri gives us a way to test our language against reality. Every future headline, every optimistic announcement, every dismissive statement about the stars can be brought back to the same question. What does this actually change when applied to the nearest star? If the answer is specific and grounded, the benchmark has done its work. If the answer is vague, the idea probably is too. So the stars do not become less beautiful under this more honest map. They become more exact. They become the kind of objects we can think about seriously, with specific constraints, specific requirements, specific timescales, rather than the kind of objects we invoke for emotional effect and then leave behind when the arithmetic becomes uncomfortable. And that is the kind of wonder the nearest star offers us. Not the wonder of vague immensity, the wonder of precise separation. We can name the target, we can model the routes, we can identify what each mission class would require, we can compare the trade-offs clearly. And after all of that, the conclusion remains both stern and luminous. The stars are separated by enough to matter in every operational sense. The nearest one shows that immediately, but showing it is not the same as closing the question, and it is the same as framing it honestly. And perhaps that is what we needed most. Not a shorter distance, a truer map. Alpha Centauri gives us that. It does not flatter us, it does not discourage us. It simply tells us what seriousness requires. And that is a harder kind of closeness than 4 light-years suggests, but a more valuable one. The nearest star earns every hard word, and the hard words are what we need before anything else. Because if we ever do reach across that gap, the achievement will mean something specific and earned. It will not be an accident of technology or a lucky simplification of the problem. It will be a demonstration that we learned, at least once, to carry understanding through a scale barrier that the nearest star has been patiently revealing all along. And that first honest step begins here, with the number 4, with the star that sounds almost friendly, and with all the physics it refused to let us skip.